Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. If you are here because you want to learn to program in Java, you are in the right place. This is the 25th video in the Introductory Programming in Java full course and the 8th and final video of Lesson 4, Looping Structures in Java. Now that we've learned about writing loops, let's talk about common looping errors, how to test code with loops, and debugging a loop. Let's get right into it. This is not going to be exhaustive, but I want to show you some examples. Looping solutions are prone to off-by-one errors, edge case errors, path errors within the loop, loops that don't execute when they should, and of course infinite loops, loops that never stop executing. We'll look at examples of all of these errors in solutions to the following problem. Design a program that obtains two positive integers from the user and computes the greatest common divisor of the integers. To simplify this program, we're going to require the user to enter two positive integers, largest first. What is typically done is simply swapping the values in the variables if the second value is larger than the first. Here is an example of a solution that computes the GCD correctly. When I run it, if I enter 1071 and 462, the program tells me that 21 is the GCD, which is correct. If I run it with two numbers that have no divisors greater than 1 in common, say 9 and 7, it correctly tells me that the GCD is 1. Now let's look at an off-by-one error. In an off-by-one error, a loop executes one too many or one too few times, or produces output that's off by one value. It's very easy to write an off-by-one error into a program by starting the loop control variable at the wrong value, by writing a test that isn't exactly right, such as using less than or equal to instead of using less than, or updating in the wrong place in the loop, or by the wrong amount, or by using the wrong math. I'm going to include this program called off-by-one-count-to-10.java in my GitHub repository so you can look at these examples of all of those off-by-one causes. Sometimes off-by-one errors can be more complicated. Here is a version of the GCD program called GCD off-by-one, which has an off-by-one error. I'll try entering 1071 and 462. And again, I'm told 21, which is correct. Now I'll run it with 9 and 7. And it tells me the GCD is 2. We know that's not correct. Neither number is divisible by 2. If you're familiar with the algorithm and compute this out yourself by hand, you'll see that it needed one more iteration to get to the correct result. Let's look at an edge case error. In an edge case error, the program works for average case values, but produces an error on a value that is at the very edge of the range of input or output values. For this problem, I've specified that the program should work for positive values. The smallest positive value is 1. It turns out that our off-by-one program also produces an edge case error. If I ask for the GCD of 10 and 1, the answer should be 1. 1 is the largest integer that divides into both 10 and 1, but the program tells me the GCD is 10. A path within a program is the set of statements that execute for a given set of inputs or for a given program state. The set of statements that executes will vary when there are programs with constructs that alter the flow of control based on conditions, such as conditional statements and loops. By a path error within the loop, I mean that the code within the loop is out of order, or some code doesn't always execute when it should, or executes when it shouldn't, resulting in errors. Sometimes it's difficult to get the code in the loop working correctly for every execution. Maybe it works correctly for the first execution and middle executions, but not the last, for example. Or sometimes it works for average cases, but not special cases, if there's additional logic within the loop. So that's why I wanted to include this as a kind of error. I see it a lot in my classes. My example here is pretty trivial because there isn't much going on in our loop, but if I run this program, GCD path error, and run it on our example 1071 and 462, it tells me that the GCD is 462, which we know is not correct. This version of the solution is called GCD infinite, and you can guess what this does. I'll run it and enter 9 and 7. And if I didn't have more to show you, we could just let it run forever. Or I could click the red box, because this loop is not going to terminate. And finally, a loop that's never entered. I'll run this and enter 9 and 7. and the program tells me the GCD is 9. So one thing you might have noticed about those is it's not always obvious what kind of error we're having. The never entered and off by 1 programs gave wrong answers, but it wasn't obvious from running the program what was causing the error. Those are common mistakes to make, but they can be difficult to debug. You want to be aware of these mistakes when you're designing your program, so you hopefully don't make them. Let's debug one of these programs so we can see how to diagnose the error, and then we'll list a few strategies for coming up with test cases so we can thoroughly test our loops. Notice that some of the buggy loops produced correct results in some cases, so it's important to design a thorough set of test cases so we can catch errors that happen only for some inputs. Okay, I have GCD mystery here. This is one of our buggy loops, but I'm not going to tell you which one. To test it, we should select a set of inputs. So I'll run it on a few inputs, and we'll find one for which it gives the wrong result. Let's try 1071 and 462. It gives the correct result, 21. Let's try 9 and 7. It gives an incorrect result, 2. So we'll test it on 9 and 7. I'm going to put the breakpoint on line 21, the top of the while loop. I don't need to step through obtaining inputs, and we can tell that it's getting past the if statement on line 20 because it's displaying a GCD and not the error message. So I'll right-click in the blue margin next to line 21 and choose Toggle Breakpoint, and I'll click the bug icon to run the program in the debugger. It's going to run normally up to the breakpoint. I'll type in 9 and 7 at the prompts. And now I'll switch to the debug perspective. Let's see what the program is doing. In the variables area, I can see A is 9 and B is 7, and we're on the test while B greater than 1, which we can see is true. I'll step over. Now we're on line 22, remainder equals A mod B, and I'll step over and the remainder is 2. Now I'm on line 23, A equals B, and I'll step over. And now A is 7. Now I'm on line 24, B equals remainder, and I'll step over. And B is now 2. So far, this is correct. With this algorithm, we want to continually take A mod B, assign the old B to A, and the remainder to B. We repeat that until there is no remainder. There's a wonderful tiling visualization of this algorithm. This example is from GeoGebra's website, but if you're interested, I recommend finding a YouTube video that shows the tiles step by step. Okay, so we're back up to the test, B greater than 1. And it is. It's 2. So we'll go back into the loop. Now, with a loop, if you put the test on the loop entry condition, you can use the resume button, this green arrow, to run the program until it reaches another breakpoint. So if you feel you don't need to watch the loop body execute again, if you have a breakpoint on the loop entry condition, you can press resume, and Java will execute the next iteration of the loop and bring us back to the top, to the breakpoint. I'll do that. And we have A is 2, B is 1, and 1 is not greater than 1. So we drop out of the loop and print the value of A, which is 2. But we weren't done. The remainder was 1, not 0. The algorithm should end when the remainder is 0. So our loop entry condition is not correct. We're not looping enough times to finish the algorithm in all cases. We want to loop while B is not 0. A value of B equal to 0 lets us know that we've finally reached B dividing evenly into A. This is an off by 1 error. We needed to execute that loop one more time. So we should change that loop entry condition. Walk through the execution mentally to ensure that's all we need to change, and then rerun all of our test cases. The debugger is an incredibly useful tool for finding errors in loops because they can be very tedious to walk through by desk checking, and the debugger can quickly jump over parts you don't need to watch execute with the judicial use of breakpoints, and zero in on the parts we need to examine. Now let's talk about test cases. Can we design a thorough set of test cases for a loop? Let's start with coverage, meaning, at its most basic level, is every line of code executed by at least one test case. That is called statement coverage, and it's the weakest form of coverage, but it hopefully makes clear what coverage means. Is what we're looking at included in the test cases, in this example, statements. So for example, if we never tested the case where the test of the if statement evaluated to false, then we'd never execute line 28, which displays the error message, and we wouldn't have statement coverage. Let's talk about branch coverage, which is stronger than statement coverage. In branch coverage, we make sure that every decision point is included in the set of test cases for both true and false outcomes. So, for example, that the if statement on line 20 is included for both true and false outcomes, and that the loop entry condition on line 21 is included for both true and false outcomes. If there were branches within the loop, we'd want to make sure they were included for both true and false outcomes. What I have here is a flowchart representing the original GCD.java program, and I've numbered the nodes. We'll focus on the loop, which is nodes 4 through 9. Node 4 is the test, and that can evaluate to true, meaning we visit nodes 5, 6, 7, and 4 again, or it can evaluate to false, meaning we visit node 9. It will eventually be false unless we write an infinite loop. There are no branches or loops within the loop. So to attain complete branch coverage of our loop, we should design a test case that will cover the path 4 is true, 5, 6, 7, 4 is false, 9, or some number of iterations before we reach 4 is false, 9. I would recommend testing paths in which the loop executes 0 times, 1 time, and many times, even though the false branch is executed in all of those test cases because they include edge cases for the number of loop iterations. Now, we might also want to consider predicate coverage. If there are different ways that the condition comes to be true or false, such as in the condition for the if statement in node 3, it will evaluate to false if any of the 3 conditions are false. We want to test that branch for all combinations of the Boolean conditions. For example, true, true, false, 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 true, false, etc. This is called predicate coverage. Now, besides testing the paths through the loop, we want to test our loop against edge cases. Remember that GCD off by 1 did not work for the edge case when the value of b was 1. In fact, there is often overlap between off by 1 and edge cases because those edge cases are often handled before the loop, in the first iteration of the loop, or in the last iteration of the loop. In our GCD program, testing a b input of 1 is an edge case. We might also consider what the largest possible integer is that the user might enter to ensure our program can handle an integer of that size. And if not, we might consider a long data type or a special data type that can handle even larger integers. Our calculations will never result in a value that is larger than the operands, but with many operations, including addition, subtraction, multiplication, division by fractions, and exponentiation, you could have a result that exceeds the memory space you allocated for it. This is an error that can result in an infinite loop if you have an integer overflow. For our GCD solution, we might also want to consider result edge cases. So in addition to inputs, we might consider a result of 1, essentially no divisors in common, as an edge case, and make sure we're testing both numbers with a divisor in common and numbers with only 1 as a divisor in common. So in your test cases, be sure to account for all branches, including the loop iterating 0, 1, and many times, and even all predicates, all ways that a Boolean condition can be true or false if possible, and test typical values as well as edge cases, both for inputs and outputs. Think about the data types you're choosing to represent quantities and make sure they can handle the size of the inputs and the results of computations. As usual, I have included an auto-graded exercise in the description of this video. For this video, the exercise is a tracing exercise on one of our buggy examples, and all of the code has been uploaded to my GitHub repository. When you're feeling confident with the concepts in this video, you're ready to move on to the next lesson. As always, have fun and keep coding.